You do not allow anybody else because we're going to do a short test, okay? After we complete the test, yes, you can admit somebody else because I don't want to give the explanation in the middle of this quiz, okay? Okay, so this is what we're going to do. I prepared 5 questions. They are very short and there is no point for that, okay? So I'm not going to give you a bad grade for that. So I just want you to realize that when I ask you to review the video, that's something that you should do, okay? And we're gonna go from that point, and I'm going to present a short explanation, short summary of the video that you were supposed to see, okay? So everybody, please get ready for the quiz, okay? It's just about the deduction of the plate bending differential equation. Okay, so there are 5 questions, multiple choice, except the last one that you have to type something. Okay, so go on, and we are gonna. I'm going to give you 10 minutes for that. Okay, please, somebody let me know if you already are able to start it. Remember, this is not worth any point. This is not worth any points. So if you don't do correctly, well, that means that you didn't review deep enough the material that I gave you, okay? Multiple choice. Let me ask somebody. Mr. Cedeño, were you able to start the poll, this short poll? Mr. Cedeño? Mr. Cedeño, can you hear me?
Yes, doctor. Good morning.
Did you see the poll?
Yes, doctor.
Okay, go on. Ms. Santos, did you see the poll? Have you started the poll?
Yes, doctor.
Okay, good. So everybody can do it. So we have 10 minutes for that. 10 minutes, that's all what we have. Please turn on your cameras if possible, please, people. Very much. So it's 7:57. Okay, so I give you 10 minutes. So please read. That's something that you should get used to it. Okay, read. If possible, turn on your cameras, people. I would like to see you. Remember, this is not worth any points, okay? So try to just do your best, okay? If you did not review the material, well, try to answer something, okay, by common sense, but that's all what I can do, okay?
Good morning, doctor. And the last question, I used to put one word.
No, one character. It's a number.
Oh, number. Okay, thank you.
Okay, you can type the number with letters, but I prefer to use the numbers. We have so far 25 people who have answered questions 1 through 4. What happens with the rest? Come on, people, at least question 1. You are 35, so 10 people are not doing anything. Okay, people, it's about 9 minutes. Hurry. Have 30 answers. Come on. Okay, we're going to stop. We're going to stop. I see that the first question, when we say, let me share the screen. Can you see my screen, people?
Yes, doctor.
Okay, so here, something which is very interesting, right, is that the z-axis points downward, right? So when you say z equal plus t over 2, that signal, you can allow everybody to come in, Misayo, please. Okay, when we say z equal plus t over 2, see, I put it this question because it's easy to get confused, because usually we get positive upward, right? In this case, in this chapter, positive is downwards. Okay, so when we say z is positive, that means that this is the phase that we're signaling, and this is the bottom phase. Okay, so it's correct. That's correct. Okay, the second question, when we say mx is positive, right? This is the convention that we're going to use. Okay, so in this case, your thumb points in the positive y direction. Okay, so when you say that mx is positive, when your thumb is pointing in the negative y direction, that means that it is incorrect. It's incorrect. Okay, this is thumb in the positive y direction. Okay, I insisted that in the other axis, right, for my, okay, your thumb points in the negative x direction. That's your positive my. So please, that's something that we should have in our memory, okay? That's the only way we can learn it. Just repeat it 1, 2, and finally you will learn it, okay? That's the only way. Third question, the units. The units of my are force. Mr. Guaman, what do you say? The units of my are force?
Yes. I put
Is that correct? It's a moment.
Say my or
my.
Oh no, that's incorrect. Mx is force. No.
Yes. Let me ask you somebody, Ms. Flores, in the third question, the units of the bending moment my are units of force. Is this correct? Ms. Flores?
Doctor, but now I'm confused. I put is F, but I think this is not correct.
Okay, let me ask somebody. Mr. Romero, what do you think? Units of my are force?
I think that is force because this moment is moment pure length.
Yes, that's the correct answer. In theory of plates, all internal forces are not expressed as total values, right? But forces or moments per unit length. So when you see, and that's something which is very interesting, right? In the next semester, we will use we will learn how to use finite elements, okay? And we're going to use a program called ANSYS, and you will see the responses, right? And sometimes you forget this little concept, right? And you say, and you come to me and ask me, doctor, there's something wrong with this because this is moment and the units are force. Yes, it's correct. Because in the case of plate theory, okay, we express internal forces per unit length. Okay, so if you ask to plot or to present result of shear force, that will give you newtons per meters. If you ask bending moment, torsional moments, they will give you in units of newtons or force only, okay? So hopefully this error will allow you to keep those in your memory, okay, Mr. Waman? Okay, let's go to the fourth question. Is correct to say mxy is equal to myx? No, it's not. There is a negative sign there, okay? And we will deduce that today. Okay, now be careful. Tau xy is equal to tau yx. Yes, that's correct. But that's tau. That's shear stress. The question here is mxy is equal to myx? No. You need a negative sign there. And we will explain that today. The final question, if we have a differential equation, partial differential equation, linear, fourth order, and all of that, how many boundary conditions do we need in every point along the edges of the plate? Mr. Vasquez, how many boundary conditions do we need?
2 boundary conditions, doctor.
Yes, 2 in every point. 2 in every point, okay? So if you have one edge, in every point of that edge, you need 2 values. Similarly for the other 3, in every point of every edge, you need 2 boundary conditions because it's a fourth order partial differential equation, okay? So if you have more than 2, that's something wrong. If you have less than 2, you're not going to be able to solve for a unique solution, okay? So those are concepts from mathematics, okay? So this is just a review. Okay, people, let's go on now with the material. We're going to present just a summary because you have the material as with a video. Can you see my screen, Miss Ayo?
Yes.
Full screen?
Yes.
Okay, good. So these are something that I suggest Miss Ayo yesterday prepared a new version of this figure, okay? And I'll try to post it so you can have it in more clear. So this is MX, this is MY, this is X-axis, Y-axis, Z-axis points downward. This is positive faces, and these are the positive direction of the internal forces. So we have shear force, but in 2 phases. So we have 2 different shear forces. Similarly for the bending moments. And also in this case, we have torsional moments. You see, this is MXY, and this is MYX. Okay. This is the external force, and the external force are expressed using the reference system, the global reference system, okay? Remember, internal forces are referred to the positive or negative faces. External forces are referred to the reference system, okay? That's something that we have said many times. Okay, what else? This is the deduction of the Hooke's law, or just a review of Hooke's law in the with the components of the shear of the stresses that we're going to be using, okay? This is the shape of the Hooke's law right now. Include 3 components of the shear stresses, I'm sorry, and 3 components of the strains. And these are the relationships, okay? So using strains, we can calculate stresses. Or as we can put it here, using stresses, we can calculate strains. again, this is something that you review in, or you discussed in solid mechanics, right? But the problem is that up to now, basically, we have worked with one single sigma x component of the stress tensor. Right now, in this chapter, we need 3, even though in general, we are interested only in 2, sigma x and sigma y, okay? So from this point and on, if you say stress or normal stress, that's not enough. That doesn't tell me much, right? You have to specify the subindex because we have different values in different directions, okay? So be careful with that. Okay, now, we said that the first step of to deduce the equation is to establish a relationship between the bending moments, the torsional moments, and the curvature. Okay, this is what we are going to be doing here. Okay, all of this is in the class notes, and all of this was explained in the video. So this is just a summary. Okay, here we have the original situation of the plate. Okay, in the plane X and Z, right? And I'm showing here a deformed situation, right? Okay, using positive value of W. Remember, W is positive downward. Okay, now here we see that this section here has rotated up to here. Okay, because we are using the kinematic hypothesis. Okay, so if we consider a fiber, okay, more or less at this position, okay, this point here moves to the left an amount u, and that u is going to be equal to the distance, okay, times the angle, which is this rotation. So u is going to be equal to minus z times dw dx. Okay, now this other section located at the position dx to the right of the previous one rotates, let's assume, a different amount. Okay, so it rotates the same amount as here, but with an increment. I'm sorry about this. In your class notes, hopefully they are more clear. This is the second derivative times dx. So this is an expansion, a Taylor series expansion that we have used many times. Now, this distance corresponds to the distance that this point has moved in the x direction. So it's going to be equal to this angle times z, and in the negative direction. So if we subtract this multiplied by minus z minus this multiplied by minus z, we got the elongation of this fiber, the elongation. So this first term will cancel, and we're going to have only this one here. So this is what we have here. So this is the net elongation of this fiber located at the position z, right? Now, if we divide this by dx, we're going to have, of course, the strain. That's what we need to calculate. So if we divide by dx, we cancel this dx, and this is what we have. And you can see that this is basically the same relation that we employed in beam theory, chapter 1. Okay? We can do something similar for the other direction, and this is the expression that we will obtain. So these are the strains varying linearly, and this was, remember, that was a way to express the kinematic hypothesis in beam theory. It's basically the same, especially in this case, since the thickness is very small, okay? So it's easy, relatively easy to defend that using experimental results in plate theory. It's really simple. It's not simple, it's easy, well documented, okay? Now, after we have this, we can replace in the expression for the stress, and this is what we have in the next slide, okay? And this is what we have. So minus z, dot second derivative, that's epsilon x. Similarly, multiplied by nu, derivative with respect to y, that's epsilon y, If we multiply by E divided by 1 minus nu squared, that's Hooke's law that expresses sigma x. So this is quite similar with what we did in beam theory. But now you start seeing that we warned you last Tuesday, right? That in plane theory, we have to be worried about two main directions, X and Y. So if we want to express rate of changes in one or two directions, we have to use partial derivatives, okay? There. Now, this was the result of an assumption, okay? We assume that the stress follows this linear relationship. But we have to set up this so that we still have equilibrium. And this is the next step. So this is the situation, okay? Is this one here, sigma x. And this distribution has to be consistent, statically equivalent to the bending moment. Why? Because the bending moment, remember, means equilibrium. So if we get a distribution of shear of normal stress, you can do any assumption that you want, right? But the effect of this distribution has to be consistent with the bending moment. Otherwise, we will have no equilibrium. And this is what we're going to do, okay? So here comes the key, okay? So we need to consider one slide of this, okay? And this slide will be, will have a width of delta y, okay? So in this slice, delta y width, we're going to integrate and we'll have the bending moment. And that bending moment has to be equal to exactly the bending moment according to the equilibrium relation, okay? So this is what we do. We take a piece of this, the width of that is delta y. This is the distribution. And because delta y is small, we can assume that in this direction, in the y direction, there is no variation of sigma, okay? Because delta y is small enough, okay? So we can say that if we multiply sigma x, for example here, sigma x here, times delta y, okay, from here to here, and in the vertical direction, it will be dz. It will give us a force. If we multiply by the arm, which is z, will give us the total bending moment. And then we have to integrate. Please, please be careful. We have to be consistent. And you see that we're assuming a positive normal stress located in the positive position. And that generates a force which generates a moment in this direction. And that is consistent with our convention. That's why we do not need a negative sign here. See, if you recall in beam theory, we integrated, but we needed a negative sign. And that was because the sign convention in chapter 1 and 2. Okay? That's why I have insisted so many times. You have to keep the sign convention in your memory. Okay? Now, what's the problem here? The problem is that how big is this delta y? We can make it very large or very small, but it has to be small enough so we can, in the y direction, assume that sigma x is constant. Since we can, it's difficult to establish that because there are different situations. What we do is we define bending moment per unit width. And that's going to be the concept that we're going to be using in this chapter, okay? That's what here. So mx is the total bending moment divided by the width of the strip that we are analyzing. So right now that we discussed a few minutes ago, from this point and on, from this point and on in this chapter, every time we say shear force, torsional moment, bending moment, whatever internal force, we express that per unit width. Okay, so in the case of My, it would be bending moment per unit width in the X direction. In this case, it's Mx. That's bending moment per unit width in the Y direction. But it's always per unit width. Okay? Now we can integrate this. And since we're assuming that the curvature is constant for the whole section, so the second derivatives will be taken out of the integral, and the result you can integrate. This is the result. This is the result. Okay? This negative sign, people, pay attention, this negative sign here is because in the definition of the sigma, we have minus z, second derivative, and all of that. Okay, so we have to be careful. Here it is. Okay, now this term here, all of this term here, e t squared divided by 12, 1 minus nu squared, basically is the equivalent to the term EI in the case of the beam theory. Okay, EI is what we define as the bending stiffness, bending rigidity in the case of the beam, right? In this case, this is the rigidity of the plate, bending rigidity in the case of the plate. It's basically EI, okay? Remember, the inertia is equal to the width, h cubed divided by 12, right? In this case, it's inertia per unit width. So I give you t squared over 12. That's what you have here. Now, in the denominator, you see a term 1 minus nu squared. That term is less than 1. So it's like increasing the rigidity. How come? Well, the thing is this. If you have bending in one direction, that action helps what happens in the other direction, right? More or less, that's the sense of this 1 minus nu squared in the denominator, okay? So there are many authors, of course. One very common way to call this term is D, okay? So from now on, D for us in this chapter means E t cubed divided by 12, 1 minus nu squared, okay? Mr. Dominguez, what are the units of D in this case? What are the units of D? Mr. Dominguez?
D or T?
Anna, D.
D is force length.
Exactly, fourth length. So we have to be careful, fourth length. So Newton's meters in the case of the International System of Units. Now here, what are the units term here in the parentheses? Miss Acuña. Miss Acuña, are you there?
Good morning, doctor. Yes.
What are the terms here in the parentheses?
The terms.
What are the units of this term? Second derivative. What are units of the second derivative?
Length.
No.
Force.
No. Miss Leon?
Yes, good morning, doctor. It's force length over length.
No. What is W for you, Miss Leon? What is this W?
Is the
Mr. Zurita, what's the meaning of W? UVW. What is this W, Mr. Zurita? Are you listening to me, Mr. Zurita?
W.
Yes, doctor, good morning. W, the derivation.
W, come on, people. What is W here?
Deflection.
The deflection, yes, the vertical deflection. Okay, so let's go back now here. What are the units of the second derivative of W with respect to X? Mr. Gomez, Mr. Gomez. What are the units of the second derivative of W with respect to X? Mr. Gomez?
Yes, doctor. Dimensional.
No. The first derivative is the non-dimensional.
The moment.
No. Let me go to somebody else. Mr. Chin Chin, what are the units of the second derivative?
1 over length.
Yes, 1 over length. So you multiply 1 over length times D, which according to Mr. Dominguez has units of FL. The result is force. And that's the unit of bending moment, total bending moment per unit width. Okay, so that's something that we always have to be aware. Okay, so finally, we make this replacement and we have this. Bending moment is equal to minus D and all of that. And we can deduce something similar for the bending moment in the Y direction. Okay, so My is going to be minus D times the second derivative of W with respect to Y, etc. Okay? So that's part of what we have to take in the first step. We are relating bending moment with curvature. Okay? Now, what we have to do now is do something similar with the torsional moment. That's what we're going to do next. Okay. For that, we have to remember that we have assumed the kinematic assumption. And according to that, this U, this motion, can be expressed as the vertical distance, Z, times the slope. Okay? So that's the relation as a consequence of our assumption. This is an assumption. In the other term, in the other plane, this is the XZ plane. In the YZ plane, you will get the deflection, or I'm sorry, the axial motion in the Y direction. So it's that. And now we can proceed to calculate gamma XY. Mr. Medina, gamma XY, how do you relate that to U and V, Mr. Medina?
Good morning, doctor.
Gamma XY. What is gamma XY, Mr. Medina? Gamma XY.
The moment is...
No. Gamma XY. Mr. Ortega, do you remember? Mr.
Yeah,
Ortega,
doctor.
Gamma XY.
Is the deformation by?
No, it's a strain, but what's the adjective there? Is the object, Miss Jurado, gamma XY? Gamma
Yes,
XY?
doctor.
Gamma XY? No? Miss
No,
Valdez,
I think-
gamma XY?
du per dy plus dv per dx.
Yes, times dx, yes. And how do you call that? What is that? Mr. Kimi? Strain, but what is special kind of strain? Is what? Anybody?
Shear strain.
Shear strain. Shear strain, yes. It's a shear strain, yes. So the shear strain is du dy plus dv dx, as Ms. Valdez said. If we multiply by G, that's the shear modulus, we have the shear stress, tau xy. Now, what we can do is we can replace this in here and that in here, and we're gonna get an expression for tau xy, and this is what we have here. Okay? So we can assume that we can interchange the order of differentiation, and that's what we obtain. Okay, so the second derivative of W with respect to X and with respect to Y, it's like a curvature in the shear sense. Okay, now, units of G, Miss Aviles, units of G. What are units of G here?
Yes, doctor. The units of G.
Go on.
It's force over length squared.
Yes, yes. Okay, now here I have that multiplied by Z, that's length. And second derivative, we know that the units of this is 1 over length. So these two cancel. So the units are force divided by length squared. That's stress, right? Okay, now we have to integrate this in order to obtain the torsional moment. Okay, that's what we do next. Similarly with what we did in the case of normal stress, okay? This expression is the result of an assumption. And the assumption is that this moves and rotates, but keeps straight. It is an assumption. And this expression is the result of that assumption. Okay, we can assume anything, but integrating this effect, this shear stress, we have to recuperate the torsional moment. That's what we're going to do. Okay, so we see here, okay, that this is the shear stress here, tau xy, will multiply by this, this area. And we see that we are going in this direction, which is the opposite to the direction of our sign convention. But we have another negative here. Okay, so we combine these two negatives, that's why we have a positive here. And again, we can integrate, and this is the result. Okay, so units are, the second derivative is 1 over length. This is length cubed. So the result of this is length squared multiplied by G with units of force over length squared. The result is force. And those are, remember, this is torsional moment per unit width, okay? We are just forgetting about the per unit width. We just call it torsional moment, but we have to keep in our memory. Please put it in your memory. Every internal force in plate theory is expressed as per unit width, okay? So that's MXY. We can do something similar with MYX, okay? And you see that if this is positive, right? And it points in the positive direction of MYX, okay? So in that case, we don't need one negative sign, but we have this other one here. So the result is going to be that we're gonna have a negative here, okay? Remember, MXY is equal to minus MYX, but tau XY is always equal to tau YX. Tau XY is equal to tau YX. M, torsional moment, XY is equal to minus MYX. Okay, don't get confused. Okay, so I insist, okay, you see here in this graph that you have in class notes, the shear stresses here try to rotate in this direction, opposite to this torsional moment. In this case, this shear stress makes you rotate in the same direction as a torsional moment. That's why we have this negative, and here two negatives give us a positive. Okay. Now here, in order to combine in the next step, okay, we have, instead of G, we have replaced by D1 minus nu. Okay, So that's the reason we, instead of having G over 6, we have D 1 minus nu. Okay? That's the reason. Okay? Now, that's the first step. So we have, let me go back. We have this, which relates the bending moment with the curvature. Here, we have torsional moments with the curvature. That's the first step. Now, the second step is equilibrium. Okay, so you will see now that in the next figure, we are going to consider the difference of what happens in the negative phase with what happens in the positive phase. It's not the same. It's like you move to another point. Okay, since you move to another point, that means that you have a different value. And these differences is expressed with the Taylor series expansion. Okay, and you see here that this is step 2. Okay, step 2 is to express the equilibrium. Okay, so this is the system. This is the one phase. And when we move from here to there, you have this change. Similarly for all the other forces. Okay, so we have 3 equations: summation of forces in the Z direction, summation of moments in the X, summation of moments in the Y direction. With these 3 equations, we're going to get one single equation to combine moments, bending moments and torsional moments. That's what we're going to do. Okay, so we say summation of forces in the Z direction. Remember, positive Z points downward. Okay, be careful. Positive Z downward. Okay, so we have shear force, okay, on this phase, on the negative phase, but we have multiplied by dy. Why? Because remember, every internal force in this chapter is expressed per unit width. Okay, so we multiply this times the width. The width is dy. Okay. Similarly, for the other phase in here, multiply by dx. And then on the on these sides, here and here, we have this and we have that. And also, we have the external force. Remember, P in this chapter is expressed per unit area. Okay? So we have multiplied by the area, which is, of course, dx dy. We cancel the result. Remember, it's an equation that we employed in the case of the beams, and that's what we obtained. Do you remember what was the equivalent equation in the case of the beam theory? Ms. Flores, do you remember the equivalent equation in the case of the beam theory, chapter 1, Ms. Flores?
The derivative of the moment is equal to...
No. Derivative of what is equal to P? Ms. Flores, do you remember that? No?
The second derivative of the moment?
No. The equivalent to this equation is a first order equation. Mr. Vasquez.
Shear force.
Mr. Vasquez, please. Do you remember what was the equivalent?
Yeah, for this case, it's gonna be the fourth derivative of the deflection.
No.
And the second derivative.
No. Please, look at what we're doing here. We're doing summation of forces equal to 0. That's all what we're doing. Hold on, just a second. Mr. Hidrobo, do you remember the equation?
En bien is P equal the derivative of the shear force.
The derivative of the shear force equal to what?
P.
No, I need something else.
Minus P.
Minus P.
Minus
dV dx is equal to minus P. You see what we have here? The shear force is equal to minus P, but we have shear forces in one phase and also shear forces in the other phase. So it's equivalent. But now the problem is that instead of one shear force, we have two shear forces. Instead of one, we have two directions that we have to worry about. This is equivalent. So you have seen these things. Okay, let's go now. Summation of forces. Let's do summation of moments. It's a little bit longer. Okay, so this is a view of the problem if we stay in a position in which we see the arrow of the x-axis. Okay, so towards us is the x-axis. Okay, and you see that on your left-hand side, you see the y-axis. Okay, so we have bending moments, which make you rotate in the x direction, and we also have torsional moments, and you also have shear forces, which with an arm generates also moments. So all of these have to be considered, okay? There you go. So we set the moments with respect to the x-axis like this. So we have bending moment and y's here and here. We have torsional moments on this face and also in the other face, in the back. And now we have on this side, we have the shear force with the arm, which is dy. Now, please pay attention that every term has to be multiplied by width. Why? Because every internal force is expressed per unit width. We cancel here, okay? And also here, some of these terms will be, for example, I did not include P, okay? Why not? Because P would be a differential term. Okay? Similarly, as in the case of the beam, okay? It would be P dx dy, that's force. And we will still need an R, which would be dy over 2. If we cancel dx dy, we still have P dy over 2. But dy is a differential term. Okay, so it's 10 to the minus 1 million. That's dy. So it's extremely small. So we neglect it. Okay, what's the result? This is the result. Okay, Mr. Tanamea, do you remember the equivalent equation in the case of the beam theory? Do you remember did you remember? Tanamea, Mr. Tanamea?
No, doctor.
Come on, come on. Mr. Carranza, help him. What's the equivalent equation in the case of the beam theory, chapter 1?
Good morning, doctor. Derivative the moment
equal to?
Equal minus shear force.
Yes, yes. So you see, it's similar. The point here is that we have a problem with the signs. Yes, because we have a different sign convention. Okay? Not only that, but in this case, we have to consider the torsional moment. We cannot avoid torsion. That's the problem. Okay? Now we can talk about that in a few in the next session. Now, that's the result of summation of moments in the x direction. Now we put in the other direction, and we can get summation of moments in the y direction, and this is what we obtain. Okay, so in your class notes, you have both figures, this and the other, watching at the towards the y direction. So again, you have mx, you have myx, you have shear force here multiplied by the distance. So everything is similar, okay? And this is the result. So we have 3 equations, and we are going to combine them, okay, to get 1. So what we do is we get from here, qx Here we get qx. Here we get, let me see if I can. Here I have qx. From here I get qy, and I replace both of them in the previous equation. And I replace here and here. So these are differentials. So if we take this and put it there, we're going to have second derivatives of the moments. And this is something that you're going to see in the next slide. Okay. That's that. So we take from here, we get qy. From here, we get qx, and replace in the first equation, which includes the first derivative of moments. Of shear forces, I'm sorry, of shear forces. That's that. Again, who has not participated? Mr. Pesantes, do you remember the equivalent equation in the case of the beam theory? Equivalent equation in the case of the beam theory? Mr. Pesantes?
Yes, doctor. Is the second derivative of the moment
equal?
Equal to...
You shouldn't doubt up to this point. Come on.
The slope, no, is
no.
No.
Mr. Villalba, do you remember the equivalent equation in the case of beam theory?
Equal to P of X.
I'm sorry, could you repeat that, please? Because I didn't get it.
It's equal to P of X.
Yes, the second derivative of the bending moment is equal to P of X. And in what case could you apply this equation, the second derivative of the moment equal to P of X, to solve what type of problem? Mr. Kimi, Andres Kimi, what type of problems can you solve with that equation? Mr. Kimi.
Good morning, doctor. I don't hear your question.
Okay, Mr. Llanos, what type of problems can you solve?
Good morning, doctor. Indeterminate problems.
Yes, determinate problems, because remember, this is equilibrium, okay? And equilibrium equations allow you to solve statically determinate problems by definition, okay? Now, what's the problem? The problem is that in general, we cannot solve these problems like this because we have many indeterminate problems. What do? We combine the two things, equilibrium plus the relations that we had before, okay? Remember, those relations come from the assumption of the kinematic hypothesis and assuming that the Hooke's law holds. It's just assumptions, okay? And this is the result. Okay, that's the third step. So this is what we have so far. These are the relations between the bending moment, the curvature, torsional moment, and curvature. And this is the relation of from the step 2. This is equilibrium. So what we do is we take this and put it in here, this, put it into there. Similarly for the bending moment, and we just simplify, and this is what we obtain. So this is the equation that we're going to use in order to analyze plate bending problems, okay? So this is a fourth order. You see that the coefficient here is 1, here is 2, here is another 1. So all of these coefficients are constant. This is a non-homogeneous problem. You see that on the right-hand side, we have something which is different than 0, okay? These are the characteristics that we have to highlight, okay? So this is something that we warned at the beginning of this chapter. It's going to be partial. Everything's going to be partial derivatives. Linear. It's very important to recognize that this is a linear problem, because what we're going to be doing is try to build, right, solutions for simple situations and then combine in order to prepare solutions for more complex loading conditions. Okay, you will see that. Constant coefficients, okay? So if we use linear and constant coefficients, that usually means that the exponential functions are going to be part of the solution, okay? Remember that if we use an exponential and the exponent is an imaginary term, you can have sine or cosine terms. Don't worry, we're not going to work with imaginary things here, okay? In the next semester, yes, in vibrations, not here. Or if you have a real exponent, okay, you can express using hyperbolic, sinusoidal, or hyperbolic cosinusoidal functions, okay? And that's the fact that we have recognized that this equation is linear and with constant coefficients, okay? Fourth order, that means that we need to specify 2 boundary conditions for every point, okay? Please be careful because in this case, we have not 2 points. We have borders, we have edges. And in every point of an edge, we have to have 2 boundary conditions, okay? Not more, not less, exactly 2. And finally, it's not homogeneous, okay? For example, in the case of Engineer Isaac, he's working with buckling, okay? Buckling of plates, right? And he works with homogeneous problems, okay? So in that case, he doesn't have this term here. And in that case, he's trying to find situations where, because of the combination of loading, he has a situation where you have doubling, even though you have no lateral load. That's buckling. But plates and the geometry that he's working is very complex and all of that. Okay? Now, in general, this is the way we sometimes read it. Okay? So this is Nabla 4W. So Nabla 4 is all of this. Okay? Probably you remember Nabla 2. Okay? That's Lagrange's equation. Okay? So this case is Nabla 4. Okay? Nabla 4, D equal to P. Okay? So that's the equation that we're going to be solving in this. Okay? Finally, before we close this session, one of the things that we need to specify here is how to calculate the stresses, right? Because if the stress gets too high, you can get in trouble. Okay, so we deduce this expression here, this one here, combining Hooke's law and kinematic hypothesis, right? That's that. And this equation, we obtain integrating this, right? In the thickness, okay? So what we can do is we can replace this into here in order to obtain an expression that relates sigma and the bending moment. What's the relation between sigma and the bending moment in the case of the beam, Mr. Chiriboga? Mr. Chiriboga, what's the relationship between the bending moment and the normal stress in the case of the beam, Mr. Chiriboga? No? It's not here, Mr. Chiriboga. Okay, let's see who has not participated yet. Mr. Benavides, help me, help me.
Good morning, doctor. In beam, it's only the moment.
Come on, Mr. Benavides. What's the relationship between the normal stress and the bending moment? Miss Puertas, help him. Miss Puertas, please help him.
Yes. Teacher, can you repeat the question, please?
No, I'm not going to repeat the question. Miss Santos, help them.
Deflation.
The integral is equal to minus y by the shear stress, normal stress and
the normal.
Yeah, the normal stress multiplied
let me ask somebody. The moment is up.
Moment.
Miss Leon, what's the relationship between the bending moment and the normal stress in the case of the beam?
The moment in Y over I, the inertia.
Yeah. Something is missing there.
The minus sign.
Minus moment Y over inertia. Here, we're going to obtain something similar. That's that. Okay, so it's the moment, Z, that's the vertical distance, and divided by T cubed over 12. That's inertia per unit length. Okay, so in general, for example, you could find books where they give you the bending moment, how to evaluate. For example, you have a rectangular plate loaded with the pressure, uniform pressure, and that will give you an expression to evaluate the bending moment here or there. With the bending moment, you can apply this equation in order to find the stress distribution in the thickness. Finally, Ms. Avilés, what's going to be the maximum value of normal stress? If you have this expression, what's going to be the maximum? What position of Z will give you the maximum normal stress in the plate?
The maximum normal stress in Z.
Yeah, what value of Z? What value of Z? You are here. What's going to be the maximum value of Z to have the maximum value of sigma?
And the neutral axis.
No, come on. What's the value of the normal stress at neutral axis, Mr. Vasquez?
It's 0.
Yes. So if you replace the Z, what's the maximum value of Z that you can take? Mr. Zurita, what's the maximum value of Z that you can take?
T over 2.
Exactly. So you are here. The maximum distance is either here or up here. Okay, so when you have a plate and push it downward, the maximum stress will be either in the bottom or in the top surface.
In the top.
Could be in the top, could be in the bottom. Okay, both values are going to be the same in this case, but with different sign. Okay, tomorrow, what you're going to be doing is you're going to install what you have already installed, strain gauges. So you're going to have values of epsilon x, okay? Epsilon x in 1 and 2 directions. And with those values, you can apply this relation and get the bending moment. And these bending moments are going to be compared with the values that you obtain with the theory. That's what we're going to obtain, okay? You're going to do 2 cases. One people will work with the simply supported case, and the other group will work with the clamped case, okay? And we're going to have a very simple loading condition, okay? With this case where we have concentrated forces, okay? So we're gonna have the rectangular plate and we're gonna put some weight within a small area, approximating that as a concentrated force. And from that point, what we're going to do is put extra weights in the top of that. See, so we can assume that this is a concentrated force, and then we can unload. We can repeat this several times in order to check values, so you have experimental results. And then you are going to calculate in your next homework and compare with those results. Hopefully, you will be close to those. One is aluminum, the other is steel. So it's going to be different boundary conditions, different material, and the same type of loading condition. For every group, you can select the point where you want to apply the loading. Okay. Okay, people. I'm really sorry about this this morning. There was this big problem in the perimeter, and that's the reason I couldn't be here at 7:10. Okay. Is there any problem? Any questions, people? Any questions? Any questions? Please, for next week on Monday, I will post something. either to read, either to see, either to investigate, to calculate, or to see a video in order for you to prepare the class. So you have the class notes. So at least, okay, you have to review the class notes, at least. Okay? Okay, if there are no more questions, then I'm sorry again, and I'll see you tomorrow, some of you, in the afternoon. What happens in the afternoon every Friday? Come on, anybody? What happens in the afternoon here? Anything in the afternoon? After lunch? What happens in the afternoon here? Yes, yes. So if you get, you think you are good enough for me, yeah, come tomorrow. Okay, bye-bye. See you tomorrow.
See you, bye-bye. Thank you, Doctor.